distinguished researcher, very well known in the field of geometrical method applied to mathematical physics. I mean, it's particularly made a contribution on Ricci flows on manifold and cosmology, renormalization group flows that I don't know what is. I'm curious because renormalization group is something different. But anyway, and it's a pleasure also for human point of view because there is took his degree here in Sapienza and under the supervision of Carlo Cattaneo, and then he went to the US and got the PhD in Rome, and then his academic career was in Pavia. As associate now as a full professor now. This is a long time, not very long, but
quite a long time.
So it's a pleasure. You is a very good colleague.
Okay, thank you very much, Mario. I'm really grateful for this honor, and doubly grateful, if I say so, because I'm sharing this with Tudor Latin, with M&MoCS, and well, and also because, as Mario was saying, this is in a sense my alma mater, and always, as you say, in my mind to some extent. I'm glad to be here again. So time goes by, so let's go to business. I need a pointer here. So I will talk about Ricci curvature, relativity, geometric flow, perhaps too much. My eyes are bigger than my belly, but let's see what, time permitting, I will be able to tell you about this. So, I wonder if I can move over there. It's better in a sense, since I know. Okay, prefer like this, so I can see what I will talk about. So this is Riemannian geometry and relativity and a few applications. In a sense, those were basic themes in Levi-Civita's research, and Ricci curvature in particular is one of the main characters featuring in this interplay between analysis, geometry, and physics. Here is the Ricci flow in its role as a Riemannian solid angle. And this is a classic subject. Really very classic, even boring to some extent. However, recently, powered by Ricci flow theory, this classical subject has undergone really remarkable developments, and as I say here, we see in conjunction a conjunction of variety of ideas from topology, geometric analysis, optimal transport, synthetic geometry, and with still ongoing effects. Many new discoveries are made, and there are many excellent reviews which they are reviews just for a few months or for a few years because they need to be updated quite recently. I mentioned Jean-Pierre Bourguignon, Olivier's, Carter Sturm, Villani, and all Ricci Flowers books, which are really a good source of information. So my idea is to, in this Levi-Civita lecture, is to touch upon some of these themes, stressing not really this stuff, but some sort of unconventional aspects that Ricci curvature still holds in store. So let me start very easy with the classical framework. So our MG, wherever in this talk, would be a smooth, compact, or complete sometime n-dimensional manifold. Typically, the dimension will be greater or equal than 3, and endowed with a Riemannian metric. I already have a disclaimer because I mentioned relativity. namely the Lorentzian case, but I will emphasize, time permitting, the relevant Riemannian aspects of relativity in the form of the Hamiltonian and divergent constraint associated with the Einstein equations. So we'll stick to Riemannian, at least for simplicity, so without jumping between Riemannian and Lorentzian, because they are formally similar, geometrically very, very different. So, and often I stress it is useful to take the blessing of infinite dimension. Infinite dimension is somehow taken with a grain of salt, if not of borax, by many people, but in some cases is really a blessing. And we know, for a number of reasons, let's say the concentration of measure, phenomena, etc. But anyway, in a sense, because things are nicer seen from far away. And so we are going to use the diffeomorphism group, smooth class diffeomorphism group in the manifold, the space of all Riemannian metrics over of our manifold. The diffeomorphisms act on metrics through pullback, and the orbit of a given metric is this beast here, and the quotient between the space of metric and the action of the diffeomorphisms in a very complicated object. I mean, the space of metric is basically a trivial object because it's contractible. The quotient is not, but we are not going to use in any sophisticated way this notion, simply in a descriptive way to frame what I'm going to say. So that's it. So the Banachek instruments of the trade are typically simple: the Riemann, the sectional, the Ricci and the scalar curvature operators associated to the Levi-Civita connection of our Riemannian manifold. Here is the Riemann tensor. Basically, here is an holonomy, so non-integrability of the parallel transport around an infinitesimal closed circuit. The sectional curvature, which is the Gaussian curvature of the geodesic surface generated via the exponential map out of a two-dimensional plane tangent space. Our sponsor, the Ricci curvature, which is simply the trace of the Riemann tensor, simply in this way. The scalar curvature, the trace of the Ricci. What I wish to stress here that these objects are equivariant under the action of the diffeomorphisms group. They are tensors, so basically speaking. Here is the typical example. However, this trivial, this seemingly easy definition are very hard to work with, and if you work with components. For instance, if we think of the Christoffel symbols as the components of SON valued algebra, this is of course value 1/4, a connection of course, we have the familiar expression of the Riemann tensor, this or this. Here we just act on one index, one of the three, and or explicitly this object here. So these are really, just working with them is very difficult. It's like drinking low-quality wine. I don't know the Christoffel beer, which is, but the Ricci Curbastro wine is not very good. But anyway. Yeah, it's amazing. You can find Ricci Curbastro. There is no Levi-Civita wine or beer, but Christoffel and Ricci Curbastro is around. So to make a long story short, we get much better insight in the curvature operators if we use, and this is provided by the expression of these quantities in carefully chosen coordinate system. This is the good idea. So, making a pun with Lorentzian geometry, we use normal geodesic coordinates. This is geometry in free fall to some extent. Normal coordinates based at point P. In this case, the Christoffel symbols at the point are 0 at that point, and you get three classical formulas, generically known as Poisson. There are other names after Poisson, but let's say Poisson formula, which provide a geometrical interpretation with an Euclidean eye of the section, the Ricci, and the scalar curvature. This is the length of the circumference of a disk, let's say. And so it's the standard Euclidean value plus correction. And these corrections are the sectional curvature. The Riemannian measure is the Euclidean measure plus correction, which exactly are provided by the Ricci curvature. The volume of a metric ball centered at P with radius R is just the Euclidean volume, this quantity. This is the volume of the unit sphere in dimension and the gamma function, basically, corrected by the scalar curvature. So this is basically a consequence of expressing the metric in Riemann normal coordinates or exploiting the geodesic deviation, the Jacobi fields. So this brings us to a sensitive appreciation of defects, namely the sectional curvature is the effect of the length of small circles with respect to the Euclidean circumference. The Ricci curvature is the distortion of the solid angle subtended by a small pencil of geodesics in the direction of a given, let's say, given vector direction with respect to the Euclidean value of the corresponding spherical sector. And the scalar curvature is the defect of the volume of small metric balls with respect to the Euclidean volume. This is as elementary as this is. Nonetheless, this is the starting point of comparison geometry approach to synthetic notions of curvature and their generalization. Namely, you would like to talk about curvatures even when you do not have a smooth Riemannian manifold, let's say simply a metric space or something like that. This is the starting point, and nowadays we have a much more refined ways of attributing meaning to what means deviation out of, let's say, Euclidean space or a space form, namely a constant curvature manifold or whatever. You interrupt me if something is not clear. Then analysis comes in. Of course, when you talk about the Ricci tensor and you understand that the Ricci is related to solid angle means Gauss theorem. Gauss theorem means Laplacian. So your right question, is there a Laplacian around? Well, indeed, from the point of view of geometric analysis, a deep insight on the nature of Ricci curvature is provided by the expression of its components in local harmonic coordinates, namely coordinates which have vanishing Laplacian in the given coordinates. These were introduced long ago by Cornelius Lenschos and put to fruition by many, even Levi-Civit, I guess, but I like to remember Denis de Tark, who visited us here many years ago, Jerry Kasdan, etc. So in those coordinates, the Ricci tensor is minus 1/2 the Laplace-Beltrami acting. I'm pedantic here, I'm not writing G sub I k, because otherwise you get it wrongly and say, come on, this is 0 because the Laplacian on the matrix is 0 by definition. No, you are not acting with the Laplacian on the tensor, on the metric tensor, but on the component of the tensor as scalar functions. So this is the point. So, and there is a nonlinear quantity algebraically depending on the metric and the first derivatives. It's interesting, so you see the inharmonic coordinates, the Ricci curvature acts as a semilinear elliptic operator on each scalar function. The metric tensor implies that the metric tensor components have maximal regularity in harmonic coordinates. There is also an interesting story behind this. You see, you get this 1/2. This 1/2 is responsible of the -2 in Ricci flow theory, and you say, well, this is just a conventional matter. In a sense, it's not. At least I like to think that it is not, because we all know that it's not just the Laplacian, it's just 1/2 of the Laplacian, who is the generator of Brownian motion, not just the Laplacian. This is somehow funny, but it is like that. So 1/2, I mean, this guy comes Wiener-like dress to some extent. So If you, moreover, this is another remark which is interesting, when you pass from normal geodesic coordinates where, we think those are the nice coordinates, they are not, to harmonic coordinates, you gain control on the components of the metric tensor in terms of the Ricci curvature rather than of the full Riemannian curvature, which is typically what you learn from studying Riemann normal coordinates. This is an important fact in geometric analysis. This is the reason why the Ricci curvature is so important. So, if you don't like to use coordinates, say, well, let's see at the Ricci tensor more intrinsically, then you stumble in the, I say, ubiquitous Legionnaire-Horowitz operator. So you take one parameter family of metrics. This H is just a perturbation. This is a germ of a curve of metrics in the space of metrics. Lambda is small. And you linearize, you take the Fréchet derivative to some extent of the linearization of the Ricci in the direction H, simply this quantity, and you get minus 1/2, of course, the Legionnaire-Horowitz operator, which is this complicated object, which is basically the Laplacian of the tensor field H plus curvature terms. You get this, which is an elliptic operator, of course. But this is diff equivariant, so the linearization cannot be elliptic because the diffeomorphism is running around, and you get a disturbing term, which is the Lie derivative along a vector field. The vector field is expressed in terms of the perturbation H to this formula, which is the Bianchi operator. The Bianchi because the vanishing of this operator, this is the Bianchi, is the operator related to the Bianchi, the contracted Bianchi identities, which play a basic role in Riemannian and Lorentzian geometry, okay? So you get this quantity. So this is the picture of what happens here. Perturb, reach, you get a slight perturbation of the solid angle, and this slight perturbation of the solid angle is related to a weakly elliptic operator. Weakly because there is a diff term which broken the ellipticity to some extent, but this term is under control because it is a Lie derivative, so it's something related to the diffeomorphism group. It must be there, because otherwise the object won't be diff equivariant. So, through the infinite dimensional looking glass and what we found there, we found that not just reach, but -2 reach is a nice vector field on the space of Riemannian metrics. Nice because we are in infinite dimension. The Ricci is symmetric to tensor, so formally is a vector field on the space of metrics. No? The tangent to a curve of metrics. Infinite dimensional, I mean, the space of Riemannian metrics is just as the smooth space, the space of smooth Riemannian metrics is a Fréchet manifold. So you cannot simply say if you have a vector, there is a flow associated to the vector. You can't. Even at the point, you must be careful in claiming that this is a nice vector. So Ricci is not a nice vector, but -2 is a nice vector because this is a nonlinear weakly elliptic second order operator acting on the metric. And this is interesting because well before the advent of Ricci flow theory, basically Jean-Pierre Bourguignon, based on a remark by André Legionnaire-Horowitz, raised the question of the existence of a flow on the space of metric associated with the Ricci tensor, thought of as a tangent vector to the space of metric. So this is somehow interesting to from an historical perspective. So another interesting point is that the Ricci operator, namely thinking of the Ricci tensor as something acting on the metric as a nonlinear differential operator, doesn't come along. And this is also the reason why the Legionnaire-Horowitz operator is so ubiquitous in Riemannian geometry. It has been observed with the wisdom of insight to some extent that the Legionnaire-Horowitz operator acts on symmetric bilinear form H in the same way that the Hodge-de-Rham Laplacian, this object, anyway, acts on antisymmetric to form. So we have this relation, which is, I guess the guy who stressed that very strongly is my friend Danov. And moreover, when you analyze the Ricci linearization, this involves certainly the bilinear form, the bilinear form H, but also a covector field, the Bianchi, and also a scalar function, because typically the covector field is a gradient. So really, we can associate to the analysis of the Ricci curvature as a differential operator, as a PDE, a multiplet of elliptic PDEs, namely the multiplet described by the action of the Legionnaire-de Laplacian on scalar, vector, and tensor function, like this. So one of the other reasons the Ricci curvature is so powerful in geometric analysis is that it doesn't come alone. It comes with all this family of differential operators. Another point, which typically is not stressed that much in geometry, to some extent, is much more stressed by people in analysis who know very well the importance of scaling, because the critical Sobolev exponent, they depend on scaling, coerciveness of geometric functionals depends on scaling. So let's say, what happens if I take the metric, a Riemannian metric, and simply multiply the metric by a non-vanishing constant, lambda. So locally covariant form in this way, the contravariant form, there is lambda minus 1. It's easy, it's trivial in a sense. The distance scales according to this, the volume scales in this way, the Levi-Civita connection is scale invariant, which is easy to check. Because there is, in the Christoffel symbol, there is an inverse metric and then a metric. The Hessian of a function is scale invariant. The Laplacian is not scale invariant because there is a trace inside of the Hessian. The Riemann curvature is scale invariant. The sectional is not. The scalar curvature is not. The Ricci is scale invariant. This is really very important. So it doesn't fill the sides of the manifold, okay? The global sides. And there is a very subtle interplay between diffeomorphisms and scaling equivariance. This is another aspect of Ricci curvature. Ricci, of course, we all know, if you have even a little familiarity with Riemannian geometry, that the important beasts in Riemannian geometry are Einstein metrics. Okay? But this further aspect, which exploits scaling, besides diffeomorphisms, put forward the fact that not only Einstein, but also quasi-Einstein metrics are important. Let me remind you that Riemannian metric is Einstein if its Ricci tensor is isotropic with respect to the metric, so it's proportional to a constant to the original metric G, for some constant rho G. Beware, this is certainly a constant with respect to diffeomorphisms group, is not a constant with respect to the scaling, because rho is not scale invariant, transformed in this way, because basically rho is the scalar curvature, the constant scalar curvature, which is not scale invariant. So you have this non-trivial scaling of this constant. Quasi-Einstein metrics I was mentioning are characterized by a Ricci tensor which can be written in this form. So it's Einstein minus a Lie derivative term of the metric with respect to some vector field, explicitly in this form. So you have this symmetrized covariant derivative. This is the Lie derivative. So some constant and some complete vector field on your manifold. The picture is because it's an ex post facto picture showing what happens when you have this quasi-invariant metric. Namely, you have a motion by diffeomorphism, some sort of cigar blowing out of the manifold, for instance. So it's interesting, always with an eye on diffusion, it's interesting to note that if the vector field in question is a gradient, namely is the gradient of a function f, then the quasi-Einstein condition becomes a form of Einstein condition on the Bakry-Emery Ricci tensor, which is relevant in diffusion as some of you may know. Namely, when you study diffusion on a Riemannian manifold, what controls diffusion geometrically is not the Ricci curvature by itself, but is the Ricci curvature times the Hessian of the heat, so to speak. So is this object here, and actually this brings into the game, since the Bakry-Emery-Ricci curvature is an object related not just to the Riemannian manifold, but to the Riemannian manifold with a measure, with density, which is not just the Riemannian measure, but is the Riemannian measure times e to the minus this function. So you have a probability measure, so to speak, on top of the Riemannian manifold. So something, you decorate the Riemannian manifold with the probability measure, if you like. So now you do some computation, and the time is short, I won't go into details. Essentially, you define this quantity here, this parameter, and also one parameter family of diffeomorphisms depending on time, beta, and you consider the solution of a non-autonomous ordinary differential equation generated by V. So it's the flow between quotations, it's not the flow, of course, of the vector field V. This is the identity for beta equals 0. And you, through this diffeomorphism, you act by pullback. I'm sorry, there is a G missing in here. There should be a G. You construct this one parameter family of metrics. This is the original metric for beta equals 0. By scale invariance and diffeom equivalence, you compute, it's very easy. You make the derivative, the tangent vector to this metric, the derivative of the metric with respect to beta. You get, again, this is just equal to minus 2 Ricci flow. Ricci flow is in here. So the Ricci flow emerges from this easy, natural example. There is no way out. When you blend together diffeomorphism invariance and scale invariance, you get automatically not just the most general Ricci flow, but a particular class of solution of the Ricci flow, which are those are the equilibrium solution of the Ricci flow. So those are the self-similar solution of, here it is, of the Ricci flow, introduced by Richard Hamilton in 1982. This is equation, okay, known as Ricci solitons, okay. This is the picture explain pictorially the meaning of the Ricci flow. It's a game between diffusion and concentration, but we do not have, this is a weakly parabolic initial value problem, which is basically a reaction diffusion nonlinear PDE, because there is a diffusion term related to the fact that the Ricci tensor is Laplacian inside, which fights against the Q term, which is a strong nonlinearity, and typically nonlinearity wins. So actually we have the most general form of the Ricci flow as a natural dynamical system on the space of Riemannian matrix. A weakly parabolic dynamical system on the space of metrics defined by deforming the metric in the direction of its Ricci tensor, which is a non-trivial vector in the space of Riemannian metric. I mean, for those who are familiar with the geometry of the space of Riemannian matrix, the Berger-Ebin decomposition, but this is technical, I won't go. This is simply explained that generally speaking, the Ricci tensor, minus 2 the Ricci tensor, points away from the orbit of a given metric. So it's not the Ricci soliton move inside. Generally speaking, the Ricci moves out, the flow goes out, generates new Riemannian structure. Not enough. I mean, this briefly touching the Ricci flow. Now let's take a viewpoint of the Ricci flow from the physics point of view. Not enough, from a renormalization group perspective, okay? The point is that quasi-Einstein metrics originated not just from Ricci flow theory, they originated almost 10 years before from theoretical physics through the work of Daniel Friedan, another good friend of mine, in the perturbative analysis of the renormalization group for nonlinear sigma model. My God, what it is that? This is just the quantum field theory avatar of harmonic map theory. And this provides you really a non-trivial point of view on the nature of Ricci curvature to some extent. The picture is somehow my rendering of a random embedding of this surface in a given in another manifold. Those are the idea of having correlation function, and random with respect to a non-existent functional measure on the space of embedding. This is the usual mantra. On the non-existent, etc., one may say something, namely it's not really non-existent. I mean, it's something that... just to mention briefly, this is harmonic map theory essentially, really a theory for all seasons. It's essentially the harmonic map energy is you have a Riemann surface, Riemannian surface, sigma with metric H. This is another H, it's not the H we mentioned before. You have a Riemannian manifold mu, this into this. And since this has a metric G, the metric G pulls back on the original surface, take the trace in the metric H of this pullback metric, and you get this quantity, which is the conformal invariant energy density of the map. It's an energy. It's generalized, let's say, the usual energy you found in many other situations. In quantum field theory, this translates into the nonlinear sigma model action. You have a coupling constant which makes this adimensional. So A is dimensionless square. This quantity A times the, let's say, the sectional curvature, absolute value, provides the scale at which you are probing the manifold with this. So this may be a little bit obscure, certainly. But I'm going to clarify the point momentarily. So it's better to, in such a framework, to use the general setting provided by Riemannian metric measure space, namely Riemannian manifold plus a probability, not necessarily a probability measure, the omega, which is absolutely continuous with respect to the Riemannian measure. Sometimes you don't use absolute continuity, but for simplicity, let's stick to absolute continuity, so there is a random derivative. And the potential F is called in physics the dilaton field. Is a name. This name, you find this name also in geometry now. I mean, it's not just a physics name. And what is the idea of renormalization group, all this business, is to put diffusive versus ballistic motion at work, as usual. Namely, the underlying strategy is to probe the geometry of a Riemannian manifold M with Euclidean quantum field theory, or say, mathematics would say, with random maps between manifolds. Random between, there are question marks, because the point, the conundrum, is really defining what means random in such a setting. Okay, at any rate, we certainly have a nice example in dimension 1, namely when typically sigma is a line, and then this is diffusive motion on a manifold, and it's rather well known that you can use diffusive motion on Riemannian manifold to reconstruct the geometry of the manifold. This basically is the starting point of non-commutative geometry by Lencon. And randomness here is with respect to the Wiener measure, of course. But here you use random motion to sample and discover something which is fixed, the Riemannian manifold in dimension 1. What happens in dimension 2, namely when you try to probe the manifold not just with points, but with surfaces. This is something. You say, I want to put this surface into this three-dimensional Riemannian manifold. How many ways I have to put that cells? If I move the manifold inside, what happens? Now it's like when you put 2 or 3 Brownian motion trajectories in space. You have constraints on dimensionality. Sometimes they do intersect, sometimes they don't, which is the geometry of quantum field theory to some extent. And so the interesting point is that if in dimension 2, if we assume the existence of a typically non-existent reference functional measure, the phi on the space of map, which is non-linear, because this is non-linear space. However, it's not true that there are no bona fide functional measure. In some cases, there are. The point is that typically there are no bona fide functional measure which are diffeomorphism invariant. This is the delicate point, typically. At any rate, simply assume then the random fluctuation with respect to such a measure of the embedding around a given classical configuration. This classical configuration is just the center of map of, you say, well, what sort of map I have to use in this setting? The most trivial one, constant maps. Again, this has to do with dimension, has to do with this phenomena of concentration of measure. It has to do with the fact that the infinite dimension, if you take a Lipschitz function, typically this is constant as dimension goes up. At any rate, so random fluctuation around a classical configuration, typically this can modify the geometry of the embedding manifold. So in a sense, trying to sample the target manifold with the surface, in a sense, can generate the geometry of the target. This is a very long story. I'm not doing justice to it because for reason of time, of course. Then this generation of geometry is done through this renormalization group argument. There is no renormalization group theory in this field because the space of map is non-linear. So renormalization group in this setting is just a circle of ideas, is a philosophy to some extent, and you have to devise a way. Typical way is called background field method, and is a perturbative approach in terms of, let's say, of some coupling. At any rate, to make a long story short, you get a flow, here depicted by this picture, beta depending, you are sampling at a given scale the target manifold, you get a flow. All this was simply, essentially, to put forward the fact that this flow, which reconstructs perturbatively the geometry in a small metric ball around the classical configuration, is basically the Ricci flow in the target. I mean, up to this is a form of Ricci flow. Okay, so Ricci flow, when it came out in the early 80s, was already known, because the Danfridan thesis predates the Hamilton paper. Moreover, Polyakov himself wrote something before, and there is a paper by Honorkamp in the early 70s which is really present about the Ricci flow, to some extent anyway. You see, so the point, as long as we kill, if we kill these high-order terms, depending on A, then we really get the Ricci flow in the TAR version, which is essentially this one. So you have a flow for the Ricci, for the metric, and the flow for the measure, for the dilaton, as we say. So sometimes, I mean, typically I mentioned the reaction term generates singularity. Here it is. In this case, this is no longer true, and this connection between Ricci flow and renormalization, and this particular renormalization group flow fails, goes down, which tells you that to some extent the Ricci flow is embedded into this particular form of the renormalization group. This has led many colleagues in geometric analysis working Ricci flow theory in interacting with people coming from theoretical physics, like myself, basically, and trying to see if it is possible to extend the non-proof by Perelman of the the geometrization conjecture, removing the surgery part, because you know the Ricci flow is Ricci flow plus surgery. Is not really a uniformization theorem for three-manifold. Namely, you have to do this nasty procedure of cutting and pasting, cutting and pasting. Anyway, another long story. And just I mentioned Perelman and Ricci. I mean, the renormalization group flow, you have a coupling telling you that the Ricci flow is embedded or not into the blah blah. But also geometers have their own coupling, which is the Perelman coupling. Namely, you insist, if you put the constraint that the measure the omega is preserved along the flow, then you get the Perelman version of the Ricci flow, which is a forward flow for the metric and a backward flow for the dilaton. This game between backward and forward really does the game, allows you to prove that in a certain sense the Ricci flow is a gradient flow, which was outstanding. I mean, it was really amazing. I mean, proving that the Ricci flow was gradient in a suitable sense. It's not gradient in a trivial sense. Moreover, you can take, as I was mentioning, you can take the renorm group seriously, and this perturbative expansion may still have some degree of validity, and we may argue that in a strong curvature regime, quadratic term may play a significant role. So there is a bunch of people, myself too, studying the geometric analysis of this equation, which is an extended Ricci flow, which is really very sophisticated, but really very hard to. And the difficulty in this is apparently is not scale invariant any longer. The Ricci flow is scale invariant. Here is not really apparently scale invariant. One problem is to understand the coupling and to interpret that geometrically in a scale invariant form. Another long story. But all this perturbative argument in nonlinear theory are difficult to handle. You have this problem of linearization stability or instability, first put forward, if I remember well, by Marsden for what concern Einstein theory. Namely, you ask yourself, if I have a perturbative expansion, even all terms, is this really tangent to a curve of solution? Typically, no, there are, because the singularity in the Huber space of the theory tells you that you must be really careful. So we have, it's not really so often realized, but we do have a linearization problem for renormalization group, because renormalization is addressed perturbatively, and we do not have, in this case, a non-perturbative renormalization group at work till now, because actually there are strong indications that you may have a really non-perturbative renormalization group at work using Wasserstein geometry, in a sense. This is really very fashionable nowadays, but it's fashionable not because everybody is doing that, because it's really powerful. This is the point. So the role of Ricci curvature, so the same I was shortly described the last 10 minutes, done without quantum field theory. So the idea is to, many of the features that I described follow from a heat kernel localization mechanism which exploit Wasserstein geometry of the space of probability measure over a Riemannian manifold. So let's very briefly, because this is very technical, I don't know how much time I do have, but I will go ahead. When you are tired, just tell me I skip. Okay. So the idea is to use a weighted heat kernel. You take a Riemannian metric measure space, Riemannian metric plus a measure, and you use the weighted heat kernel associated with that, which serves at a given point of your manifold and to generate an injective embedding of your Riemannian metric space, let's say of our Riemannian manifold for simplicity, into the infinite dimensional space of all probability measure. Okay? So this is done, you take the point and associate the heat kernel measure. I had to put the measure in front of that, but it's obvious. You associate to the point the heat kernel with source at a given point. This is not the first time you use heat kernel technique. In geometric analysis, they're really powerful to, for instance, improving the so-called BGG principle in spectral theory over Riemannian manifold. But this is really something quite nice, at least in Ricci flow, certainly in normalization group flow. You topologize the space of probability with the Wasserstein, the quadratic Wasserstein measure, and to my knowledge, for the pure Riemannian case, this was nicely done in a remarkable paper by Nicola Gigli and my dear friend Carlo Mantegazza. Very nice, very remarkable paper. And I did something sort of peripheral, extending the theory to the case of Riemannian measure spaces, especially with application to the normalization group. The point is that this is not difficult to prove, but it's not really easy. Let's say you can do that. That the map, this mapping is really an embedding.
I understand this point. So you have a probability space, the Wasserstein distance over there.
Yeah.
I mean, the case of Riemannian case, what it means in the space of probability measure
over your Riemannian manifold, yeah.
And the Riemannian measure is given by the tangent space given by the Wasserstein metric.
I mean, the only difference here is that when you define the quadratic Wasserstein distance, you use as a cost function the Riemannian distance squared. That's it. The only difference is that one. So it's, I mean, this is an obvious extension of the trivial, the formal embedding of the manifold in the space of probability measure, again with the Wasserstein, that associate to X the Dirac measure over X, which is an embedding in the obvious transportation plan.
Doing confusion because the probability is a probability measure space. There is some effort to define as a Riemannian manifold with the metric given by the tangent space.
Yeah, that's right.
So this is what.
Yeah, that's right. There is an auto potential coming by.
Yeah, exactly.
And the point is that I can pull back via the map I over P the Wasserstein distance from here to a distance on the Riemannian manifold. And the amazing fact proven originally by Carlo Mantegazza and Nicola Gigli is that this pullback distance function is Riemannian, comes from a Riemannian metric. You can write down the Riemannian metric. Where it is, I'm sorry. Should be, I'm sorry, anyway, there is a formula for the Riemannian metric. I'm sorry, I apologize. There should be a formula that for some reason disappeared, I forgot to put it down. Anyway, it's a time-dependent Riemannian metric, and the point is that I wish to make rapidly. The difficult part of their proof is that you have to show that this Riemannian metric, as t goes to 0, reduces is really a deformation of the original Riemannian metric. Namely, as t goes to 0, you recover the original Riemannian metric, but of course, for t different from 0 is something else. Now, t going to 0 is a very singular limit. It's very difficult to handle, but they managed to handle that and prove. Anyway, in general, you have this inequality, which is a basic inequality in Wasserstein geometry, namely bounding, this is the reason why the Ricci curvature is so important, because the lower bound of the Ricci, of the Bakry-Emery-Ricci curvature is the object that controls diffusion, that controls everything when you do this game of using the Wasserstein distance. And so you have this inequality, which is very nice. At any rate, you take, for almost every t, there was a technical issue here, you really compute the tangent to this metric as t equals naught. And you recover, I mean, they did, Carlo and Nicola did that for f equals 0, namely for the pure Riemannian case, getting this equation, namely just R. I did the same for the general case. You get this. This Q doesn't really matter. It's a trick for transforming a Riemannian measure space into a Riemannian space. Namely, you warp the manifold with a Q-dimensional flat torus and let Q go to infinity. This is a standard trick in Riemannian measure spaces, namely using quasi-infinite dimensional Riemannian geometry to deal with measure on a Riemannian manifold. And you get essentially the tangency at t equal naught looks like the Ricci flow equation, but this is just for t equal naught. So when I remember discussing with Carlo Mantecazza and Nicola, he said, well, why don't you try to prove that in general you get a new flow, not just a t equals 0. Of course, people doing hard analysis in metric space, they do not like to do computation. I don't know why, at any rate. And but we know, I mean, certainly Tudor knows very well that there is a wealth of important results in the geometry of diffeomorphism group, which carries on a weak Riemannian structure, and the Arnold school, and I mean, it's funny that people working in optimal transport, let's say John Lott, for instance, there is a paper, recent paper, computing the Riemannian geometry on the space of absolutely continuous probability measure of a Riemannian manifold. So you are not in the setting of a full Borel measure, but just in a dense subset, and discovering what is the Riemannian curvature of this space of probability measure, blah, blah, blah. Long CMP paper, very nice. I use that. It's amazing that the same results were obtained more than 10 years before by the Arnold School. I mean, they have been published in the Siberian Journal or whatever, but they were there. On anyway, this is technical, but so it's amazing. And to make a long story short again, I decided to embark in the computation, and I was lucky enough to compute data. So we really get an extension of the Ricci flow, in this case, if we confine ourselves to the subspace of the space of probability measure on a Riemannian manifold, but the subspace of absolutely continuous probability measure with respect to the Riemannian measure. The difficult part of this theory is to extend this to the space of full probability measure, namely not assuming that there is an absolute continuity with respect, namely you, whatever, delta, etc. So you have a big issue. What are the properties of this extended Ricci flow? This is a full renormalization group flow. You go, I mean, you can construct an abstract Wiener measure a la Gross on this space and prove you get a functional. We generalize the Perelman functional, the entropic functional. You can prove that this functional is a large deviation functional for the system. So you are in a full renormalization group setting from a rigorous point of view. This is not perturbative. This is a full. In my opinion, this is, it's like when you do quantum field theory, you use Gaussian measure. So you have which is somehow trivial, and the real field theory is a singular perturbation of the Gaussian measure, the Wiener measure, or let's say generalized Wiener measure. Here is the same. This is somehow a trivial, between quotation, renormalization group, Gaussian-like, so to speak. The real renormalization group should be a singular perturbation of this object. Of course, I don't know how to do that, and not even Nicola or Carlo are able to anyway. If I have 5 more minutes and I conclude, because I say with relativity very rapidly. So back to our sponsor, because Ricci has always liked it best in the Lorentzian signature to some extent. So many subtle mathematical aspects of general relativity are related with the study of initial data sets for Einstein equations. The Einstein equations simply are the Einstein-Levi-Civita equation. In Italy we say Einstein-Levi-Civita equation because apparently it was Levi-Civita who suggested to Einstein this form of the left member of the Einstein equation, because Einstein was insisting very strongly on using just the Ricci tensor, so strongly that he was also renouncing to the diff equivariance to some extent in order to comply with this idea. Then Levi-Civita, and there is an exchange of letters where Levi-Civita showed that this must be the proper tensor because this satisfies the Bianchi identities, and this will imply that the system is freely gravitating, namely that the evolution equation of the sources, or the sources here, follows are a consequence of the field equation, and they are not imposed by hand. This is the basic tenet of general relativity. So it's interesting that the constraint set for Einstein equation have very strong seminal interaction with geometric analysis, minimal surface theorem, mean curvature flows, positive mass theorem, and the Yamabe problem, Yamabe conjecture, probably many of you know, was proved by using ideas coming from this setting in by Shen and company. He's reminding me that it's time to close it anyway. So the Einstein equation, if you are not familiar, I don't know, to get some familiarity, let's compare with Maxwell electromagnetism. So the 4-dimensional space-time metric, let's think as a 4 potential, the vector potential and the scalar potential. The 3-dimensional metric of physical space, where we live, to some extent, is the electromagnetic analogous to electromagnetic vector potential. The local geometry of time is called n, the lapse function, is related to the scalar electrostatic potential. So here the familiar form of the Maxwell equations that you might put in manifestly covariant form using the Faraday tensor. Here the not so familiar form of the relative Einstein equation along as a dynamical system. Do not mind about the evolution. This is the evolutive Maxwell part. This is the evolutive Einstein part. Those are the Maxwell constraints telling you that you cannot freely choose the electric and the magnetic field on a given slice and propagate them in time. You have to comply with those constraints, solenoidality and divergent constant here. Analogously, you have propagation equation for Einstein, and you have this set of constraints that parallel this. K is the extrinsic curvature of the bedding, rho is the density of matter, J the density of current of matter. This is, you can work out, this is the object. This ends up in being an undetermined elliptic system of equation. Namely, there are many solutions to this equation to some extent, many interesting solutions. Okay, so this is the reason why it's so interesting from the point of view of geometric analysis, quite beyond relativity. I mean, it's an interesting being. The carrier of Einstein data is an important property of a Riemannian manifold. As important, almost as being Einstein or as being whatever, something else. So what happens is that when you have data, initial data, satisfying those constants. Say we have two sets of data, blue and red. What can we do with them? So in the physical relevant case, they can be the Einstein evolution, the blue one can be the Einstein evolution of the red one, because as in electromagnetism, these data are in involution. One can be near to the other in some geometrically relevant topology, in the phase space of the theory, stability issues. One can approximate the other in some constant preserving scheme. This is important in numerical analysis, numerical relativity. This is important, for instance, when you try to generate the templates for understanding the form of the gravitational waves. These objects are not just an exercise for mathematicians. Those are the objects of the trade in gravitational wave theory, experimental, namely find the templates telling these waveforms come from two black holes or come from two neutron stars or something like that. So finally, the idea is that one can be Ricci flow conjugated to the other one. Namely, you can use Ricci flow theory. This is the constraint submanifold for Einstein theory. This is submanifold, infinite dimensional submanifold in the phase space of Einstein theory. And of course, the Ricci flow doesn't move in this constraint submanifold, nothing else, because the Ricci flow is weakly parabolic, whereas the Einstein flow is weakly hyperbolic with an elliptic edge. But you can use the Ricci flow to interpolate. You move this way, and you can, the point is that this Ricci flow interpolation is a geometrical averaging of initial data with many, many nice properties. You can there are even consequences out of that. And I simply mention this because this is an essential point where the fact that the Ricci curvature is a multiplet of operator, not just the Ricci linearization operator, you use that. Namely, you propagate one data set. One data set is a scalar, vector, and tensor. You propagate with a forward Lichner it operator. This is a parabolic forward operator. And you back propagate the other data set with a backward it equation of this form. This works wonder. It even generates the it kernel for the Ricci flow, which is amazing. Of course, there are it kernels for parabolic equation where the leading coefficient depends on time. The Lanconelli is a typical example, which is somehow tricky, but anyway. So Ricci flow is a parabolic averaging of an initial data set with many natural properties, and I skip on that because it's time for concluding. This is just, just mentioning this work. So what was at stake in this talk? So a selection of themes that shows the Ricci curvature as an enduring source of new ideas in geometry and physics. Ricci and geometric analysis on spaces more general than Riemannian manifold, so not so unexpected role of the it kernel on Riemannian metric measure spaces. Leading role of Ricci flow and its extensions as a guiding principle in this analysis. Connection with the circle ideas associated with the renormalization group flow and quantum field theory. The multiplet nature of the Ricci operator, averaging of initial data in general relativity via parabolic conjugation induced by Ricci flow. All this provides indications that there is a lot of territory to explore and the research worth of pursuing. And just as a personal note, if you allow me, I had the good fortune here, for instance, to be in a time and places where these persons were comfortably encouraged by teachers as remarkable as Carlo Cattaneo and my good friend Wolfgang Windler. Thank you very much.
Thank you for succeeding in containing in a reasonable time such huge amount of information.
Too much.
There are questions?
I'm sorry, anyway, it's funny.
Mars.
You mentioned the soliton. Where is that? A Ricci soliton.
Sure. There is a soliton, yes. I mean, you move by diffeomorphism and scaling. So what happens, of course, scaling grows, etc. What happens is that you, this movement of deformation, let's make a trivial example, which is not really what happens because it's too complicated. Typically what happens, solitons are, you have solution, you start like this, and this, etc., goes along with time. And another trivial idea is simply, I'm using the bedi, which is somehow trivial. Think of this manifold, okay? So there is, suppose this is a sphere, you put a hand inside in here, and push here, move your hand. So this bump moves around continuously. You get a diff soliton, which the geometry remains the same, but you have this soliton. This is trivial. This is not trivial. Moreover, they have a very basic role in Hamilton theory, Ricci flow theory, because they model the singularities. Because if you blow up the singularity, this is a parabolic equation basically, so you can blow up the singularity. You think the singularity are nasty. In reality, blowing them up shows you that the singularity are very nice to some extent. Up to one, which is the Broder singularity, the scar, which was a stumbling block in Ricci, in Hamilton's program, and one of the basic contributions among many by Perelman was to show that you don't have this sort of soliton messing you around. You don't want a solution that goes over and over with this, so to speak, but anyway. So, but there are, I mean, Ricci soliton theory is really very, just studying Ricci soliton is really very complex. You have a very complex landscape, proving that the Ricci soliton is gradient, non-gradient, especially when you move up in dimension. In dimension 3 they are classified. Thank you.
Some other questions, remarks? So if not, then thank you.